So I will hand over to Saskia.
Hello, good afternoon, everybody. Welcome to this week's colloquium. I'm very happy to have Ravit Helled here. So Ravit got her PhD in 2008 in Tel Aviv, then moved to the UCLA to work on planetary science. So Ravit is an expert on planet formation, planet evolution, and planet structure, both for planets in the solar system and exoplanets. So she's trying to combine all these things together. She started most of her work on this in UCLA before moving back to Tel Aviv for a couple of years, where she was assistant and associate professor. And then since 2016, Ravit is in the university in Zurich, first as an associate professor, and then since 2023 as a full professor. And I think the one prize that I really want to mention, Ravit doesn't want it, but it's the Paolo Farinella Prize for outstanding contributions into the internal structure of planetary bodies. And I think this is also where she's going to talk about. So Ravit, floor is yours.
Yeah, thank you. So welcome everyone. Maybe the lights we can make a little bit. Okay, good. So thank you for being here. I hope you're not going to regret it. I got an email saying that the students should attend these seminars. It's the same for us. So this talk is mostly for the students. So I'm sorry for my colleagues, but anyway, good. So I'll start. So I'm going to tell you a little bit about some recent developments on our understanding of giant planets in general. Okay, so I'm really happy to be here, and I also want to thank my students and postdocs and collaborators, because without them, this work, wouldn't have been done. Okay, so I think some of you already know, but I will repeat it anyway, that there is the field of exoplanets, which is a still relatively young field in astrophysics. And until the mid-90s, the only planetary system we knew about was our solar system. And therefore, all planet formation theory was tuned to explain what we see in the solar system. Of course, things have changed after the discovery of the first exoplanets. Then we realized that, planetary systems are very diverse. In 2000, in addition to radial velocity, we also had transit, so suddenly we could get information about the size of the planet and not just the mass. And then, of course, when we have mass and size, we can do something about mean density and start to characterize this object. And today we have thousands of exoplanets that we try to characterize and use those to understand how planets form, what determines the architectures of planetary systems, and so on. So you see the field is 30 years old, but we still have many open questions. So how do planets form? We still don't understand the formation process of planets. What is the occurrence rate of planets? So we know that on average, around every star there is a planet, but we want to understand what determines the existence of planets. What are the compositions of exoplanets? So again, we detect them, but then we want to know what they're made of. Of course, we are looking for Earth analogs, so we want to find habitable planets or planets that have at least liquid water on the surface. We still want to understand the composition of the planets in our own solar system. They are still poorly understood. And also to just answer, is our solar system unique? How unique it is to have a planetary system like our own? So these are kind of the burning questions, and we are still making a lot of effort in answering them. But in this talk, I'm going to talk mostly about giant planets. So they are not habitable. Maybe their moons are habitable. But why is it important to study giant planets? So the first is because they shape the architectures of planetary systems. They are the first planets to form. They are very massive. They have dominating gravity. So basically the shape, or they influence the formation of other objects in this planetary system. Then also their composition, because they are hydrogen helium dominated. By understanding their composition, we can better understand the conditions existing in protoplanetary disks where planets form. And then, last but not least, they also serve as natural laboratories to understand how material behave at high pressure. This is our chance to explore different compositions at very extreme pressures and temperature because they're very massive, right? So they reach conditions that we cannot reach on Earth unless we have very specific experiments. And in addition, until today, they are still the best planets we can characterize just because of the quality of the data. So it's much harder to characterize small planets. And here you can see the planets in our own planetary system, and you clearly see that our planetary system is dominated by the gas giant planets. Okay, so why is the formation process important? So why do we need to study how planets form? Well, because that tells us where planets form, how long the process takes, and then it also tells us under what conditions we expect different planetary types. So it's very important to explore the formation process of planets, and you have here in Heidelberg many researchers working in this direction from different angles. But it's not just the formation of planets that is important. The thermal evolution is also very important, and this is because even if we understand the formation process, which we don't, but assuming that we do, as the planets evolve in time, the internal structure can change. And there are different physical and chemical processes in place that can influence the current state internal structure. Okay, when we look at planets, they are old most of the time. So we need to understand how things change with time. And this is why we really need to understand the evolution, which can help us to understand under what conditions we expect planets to be convective, under what conditions we expect them to have layered composition, layered structure, and so on. And this is where, for example, the time element is very important, and we are going to have, for example, the Plato mission help us to better constrain the age of the planets. So again, the evolution is important because it tells us how the internal structure changes with time. And it also affects the cooling. So if I know how heat is transported, I can model the evolution properly. So that means that there is a clear link to the internal structure itself. And why do we care about the internal structure? Well, because the inferred composition strongly depends on the assumptions of the internal structure. And when it comes to giant planets, typically, the end member structures are core plus envelope or homogeneously mixed, but now we also realize that there are some other more complex structures like composition gradients, what we call fuzzy or dilute cores. And as I said, depending on your model assumption, you will get different metallicity for your planet. So this is why we have to take that into account as well. So actually, these three aspects of planet formation, evolution, and internal structure are really interconnected. So what we try to do is kind of understand those links and consider them in one kind of theoretical/numerical framework. Okay. Then there is the aspect of the solar system planets versus exoplanets. So when it comes to the solar system, well, we are lucky because we can send spacecraft and make very accurate measurements. On the other hand, for example, when it comes to gaseous planets, we have only 4 of them, right? So we cannot do statistics. When it comes to exoplanets, well, we have many more, but if we are lucky, we have mass, radius, age, and atmospheric composition nowadays. But it's still not easy. So the idea is to kind of take these 2 different types of data, let's say, in the solar system and for exoplanets and try to put them together to better understand giant planets. And here you just see some facts. So for example, in the solar system, as I said, if you were thinking about giant planets in the early 90s, you would think, it's actually a very well-behaved system. Giant planets always occur further out, in large radial distances. There is some kind of nice behavior that the mass is decreasing with increasing radial distance, and that there is an inverse correlation between the mass of the planet and the metallicity. So the more massive you are, the more metal poor you are. And then with giant exoplanets, we see much larger diversity. We see the giant planets can be very close to the star, very, very far from the star, very different compositions, and so on. Of course, we also now have some statistics on the occurrence rate of giant planets around different stellar hosts. So, how it depends on the mass of the star. So the more massive the star, it is more likely to have a giant planet and also higher metallicity. Okay, so what about how do we model planet formation? So this is really kind of 101 planet formation. So what do we see here? So here you see a framework of what we call the core accretion model. What you can see here is the mass in Earth masses, and typically the time is given in million years. You don't have numbers here on purpose because it's very model dependent. So of course one can manipulate the model as we want to kind of change the numbers. But the concept is still robust and is the same. Okay, so what do we see here? So let me explain. So we have these different curves. So this red curve corresponds to the heavy element mass in the planet. Here we have the hydrogen helium mass, which we often call the gaseous mass, and then the blue is the sum of these two curves. Okay. So what do we see from this figure? So we see that at early times, most of the planetary mass is the heavy elements. Okay, so it's mostly the core, and then there is a slow increase of the hydrogen helium mass with time. At some point they cross, and then the planet becomes hydrogen helium dominated. So this is known as crossover mass. And if you manage to reach this point, you can form a gas giant planet. The reason that this model is so popular, it's because it's very, very intuitive. So depending on when you stop your formation process, you can end up with being a terrestrial planet that is dominated by heavy elements. If you stop somewhere here, you still have some hydrogen and helium, but you still have a lot of heavy elements, so you end up with something like Uranus and Neptune. And as I said, if you reach crossover mass, you will have a giant planet, let's say like Jupiter. So depending on the exact conditions and how much time you have to form your planet, you can explain the diversity of the many planets that we see. Well, in the solar system, but also around other stars. So that's, again, the idea. Depending on the accretion rates and how long it takes you to form and where you form in the disk, you will end up with different planetary type. So that's very intuitive. That was kind of, I hope, the introduction for planet formation. And just to be fair and say that this model is nearly 30 years old, and although we keep working on it, the basic principles remain the same. So here you can see an example from a very famous paper from Pollack et al. 96, and here you can see it's a specific model that aims at forming Jupiter, so forming a giant planet at 5.2 astronomical units, and here you can see the age, it's in million years, and you can see, well, how long it takes Jupiter to form. Of course, at the time we didn't know that the average lifetime of protoplanetary disk is a few million years. Now we would feel quite uncomfortable with this 8 million years on this figure. Another thing to point here is that here you stop, basically, you would think that the planetary mass goes to infinity, which is clearly not the case. At some point, the planet stops accreting. So one can, play with the model, and if you want to form your planet faster, you can play games with, let's say, opacity, because what determines this gas accretion rate is actually the contraction of the planet. So if you manage to radiate the accretion energy faster, you will contract faster, and then you can accrete more gas. So for example, if I reduce the opacity in the atmosphere substantially, I can accelerate the formation process. So this is just an example of a model that aims at forming Jupiter. So you can see, okay, we can form it super fast if we wanted, and then you kind of reach the desired mass of your planet by saying that, okay, either it opens a gap or the gas dissipates and so on. Okay, so that's kind of the introduction for the formation process. But I want to say that in these older models of planet formation, in order to make the calculation simpler, it was assumed that the heavy elements that are accreted by the planets go all the way to the center. So they go all the way and form a core, like a heavy element core. Even at that time, the authors knew that this is a simplification, but they just did it because numerically it was much easier to solve the problem. In fact, they could see that when you accrete the heavy elements, which could be in the forms of planetesimals or pebbles, they would actually stay in the envelope at some point and will just vaporize there. So that means that the distribution of heavy elements that you expect from the formation process is not of a core plus envelope, but something that has kind of composition gradients, like you can see here. So here you can see Z, so the heavy element mass fraction, and this is a function of planetary mass. These are just for different type of models, and you can see that there is a kind of a continuous decrease. So you have composition gradients. And for those who work on, let's say, stellar evolution, you can already imagine that if you have composition gradients, it can also mean that you can suppress convective mixing, for example. So that would also mean that you have a different evolution. But the important things from this calculation is that we now know that there is no such thing as a very well-defined core in giant planets, but you have something that is more fuzzy. So there is no clear place where you would say, okay, this is the core and this is the envelope, because you have a gradual distribution of heavy elements. And how exactly this distribution looks like, well, that depends on the accretion rates of the heavy elements and the gas. And what is the the bulk metallicity of the planet? Well, it depends how many heavy elements you accrete during runaway gas accretion, when most of the planetary mass is gained, or after the formation process. So this relatively low envelope metallicity could go up and down depending on the composition of the gas that you accrete and depending on how efficiently you can accrete heavy elements while you are forming or after the planet has formed. Okay, so that's kind of the planet formation idea. What about the composition of giant planets? Well, actually, this is where we can use quite simple models to end up with quite deep insights. So what do I show you here? So here you see the radius in Earth masses, in Earth radii versus the mass in Earth masses. And here you see two theoretical curves for a mixture of hydrogen helium without heavy elements or without a core. And here is when you end where you add a 15 Earth mass of a heavy element core. So then you can draw these curves. I mean, they are theoretical curves, and then you can put the measurements of the planets in the solar system. So we have Jupiter and Saturn. And what do we see? Well, we see that both Jupiter and Saturn are smaller than what we would expect from a pure hydrogen-helium mixture in protosolar composition. So just by that, the fact that they are smaller tells me that they are enriched with denser materials. Okay, so this I can already say that they don't have a solar composition. And then when I look at the second curve, which is 15 Earth mass of heavy elements, I can see that then Jupiter fits pretty well, but Saturn is still smaller. So that tells me that the relative enrichment in heavy elements is higher in Saturn compared to Jupiter in relative terms. So I can already conclude something about the composition of giant planets just by putting them on a mass radius diagram. And this is why when it comes to exoplanet characterization, we often use the mass radius diagram. It doesn't tell us the composition exactly, but it gives us kind of guidance in terms of the composition. Of course, in order to model the planets properly, we really need to understand, as I said at the beginning, how the composition or how materials behave at high pressures. And this is why we work very closely with the high pressure physics community, because we want to understand the equation of state of, let's say, hydrogen, helium, and heavier elements in planetary conditions. So another example of quite a deep conclusion we can make just by looking at phase diagrams, or like the phase diagram of hydrogen. So here you can see that's the phase diagram of hydrogen. We have the temperature in Kelvin versus pressure. This is in megabar. And you can see, so here we have like molecular fluid. So this is H2, I think the most intuitive thing for us. And here we have atomic fluid, or what we called metallic hydrogen. And here you can see solutions for Jupiter and Saturn. So what do we conclude by just putting these curves on the phase diagram? Well, first of all, we can conclude that giant planets are fluid because they don't reach the point of solid hydrogen. And then we can also see that their solution crosses to the atomic fluid regime, which tells us that this is the place where hydrogen behaves like a metal. Right, so basically you have free electrons and you have high electrical conductivity. So that already tells you that you should expect to have strong magnetic fields in giant planets, which is indeed the case. And this is not because of an iron core like we have in the case of Earth, but it is because of metallic hydrogen. So is again an example of how you can actually reach quite deep conclusions by looking just at simple connections. Okay. So there is, of course, a small complexity because actually we don't just need to understand the hydrogen equation of state. We also need to understand the interaction between hydrogen and helium. And apparently it's not so easy because at some pressure temperature regime, helium likes to separate from the hydrogen. So we are in a situation that we have helium rain. So basically, helium from the outer part of the planet would sink down, like will rain out to the deeper interior, which would tell you that the distribution of helium inside the giant planets is not non-homogeneous. So this is another complexity, and because of this process, also the evolution of the planets is affected, and this is because you kind of convert to some extent potential energy into thermal energy, so that affects the cooling. And here you can see a figure that shows the differences between a homogeneous evolution when you don't account for this process compared to an evolution when you do account for the process of helium rain. So that makes it more complicated. And again, when it comes to exoplanets, often it is ignored. When it comes to the solar system planets, when we have very accurate data, we have to consider those processes. Okay. So in the solar system, as I said, we have really accurate data because we have spacecraft going there and we can measure the magnetic field to very high order and the gravity field to very high order. And then we can basically make an interior model. So we solve standard structure equations. Of course, we have to make some assumptions. We need to decide what materials we want to use, but typically it's hydrogen, helium, plus some heavier elements. And then we try to make a model that fits the gravity data. Okay, and the gravity data that we have for, let's say, Jupiter and Saturn is the gravitational moments, okay, that basically that give constraint on the way that the density is distributed within the planet. So you can see, which you can see it in the slide here. If you don't know exactly what it is, don't worry about it. But these are the contribution functions of the different gravitational moments. And basically you can use those measurements of the different J's to get something about how the density is distributed. Okay, then suddenly you have much stronger constraints. And this is really what we do for modeling the giant planets in the solar system. Of course, the better the data, the harder it is maybe to find a solution. And again, I have to remind you all that it's not so easy because the equation of state is complicated. You know, Jupiter, for example, high up, it's very fluffy, it's cold, it's low pressure, but deep inside you have very high temperatures, very high pressure. And you need to account for these transitions. You need to account, as I said, for the hydrogen-helium interaction. You need to understand how the heavier elements affect the equation of state, and so on. So we still make simplifications, right? It's very symmetric. We typically ignore rotation, but we try to do the best we can. Of course, again, the better the data, the less freedom we have in the modeling. And until relatively recently, since we did not have dedicated missions, we had quite a few models that were acceptable. And we were kind of happy about that. But then with Juno and Cassini, we realized that with the old models we have, the old interior models, that typically had a core plus envelope structure or homogeneously mixed structure, we couldn't fit the data. And then for Jupiter, we had very accurate gravitational gravity data. For Saturn, we actually had even information from ring seismology. So this was even further constraining the internal structure. And in order to fit these two different set of data, there is only one way to do that, and this is where you have composition gradients in the deep interior. So here you can see this is for Saturn, the heavy element mass distribution that is consistent with the data. It's still, of course, degenerate. You don't have one solution, but you need to have this composition gradient, and the same is for Jupiter. So it was really, it was a revolutionary discovery, because until that point, we thought it is okay to model giant planets as kind of simple objects. And both of these planets in the solar system told us that this is not the case. So if there is something that we could conclude, is that giant planets are non-homogeneous, they are not fully convective, and they have composition gradients. Okay? so that means that it's much harder to model them. But the nice thing about it is that it gives us some kind of link between the formation process and the internal structure. And I just said that, formation models indeed predict that we have composition gradients because of the accretion of solids and gas together. Okay, so this is when it comes to the solar system giant planets. Of course, it's different for exoplanets because, as I said, we don't have so much information. So there, what we do is really we take the concept of mass radius diagram, and this is pretty old by now. But here you can see hydrogen helium curve at different radial distances, and here you can see these are the hot Jupiters that were discovered. And what are the hot Jupiters? They are planets that are just more inflated than what you would expect for a just protosolar composition of, in terms of hydrogen helium. Even if you would put pure hydrogen, which you cannot form a planet of pure hydrogen, it would be still too inflated. And this is really where the concept of hot Jupiters was kind of was born. And then what we do is we put these different compositional curves. Again, of course, for terrestrial planets, you compare it to iron rock, like composition, and so on. And when it comes to giant planets, you try to essentially determine the heavy element mass in the planet. So you always take hydrogen helium in protosolar composition, which is kind of universal, and then you play with the heavy elements. And this is what we do. And now we really have quite a lot of data. So we can play with the metallicity of the planet and see how it depends on the planetary mass. So for example, here you can see how the heavy element mass changes with planetary mass, and we can see some trends. Of course, there is a lot of scatter, but we do find some trends. So basically, the more massive the planet is, here you see it in total mass. It's not relative. It's not the heavy element mass fraction, but we find that the more massive the planet, the more heavy element you have. But at the same time, the metallicity of the planet is inverse proportional to the planetary mass. So it means that the smaller the mass is, the more enriched it is with heavy elements. And this is what we see in the solar system, right? Like Earth is essentially 100% heavy elements. And Jupiter is mostly hydrogen helium. Okay, so we do play these games, and there is a lot of scatter, and here you can see just a comparison between core envelope versus fully mixed and different equation of states. So of course that also affects the statistics. And now when we have better data, we realize that again we need to say goodbye to the very simplified manner of modeling giant exoplanets. But let me go back to Jupiter and Saturn. I said that now we had really accurate measurements of these planets, and we concluded that both planets are non-homogeneous, are not fully convective, and could have, these fuzzy cores. But if you think about them in normalized mass, and you plot all the solutions or some of the solutions in the literature, and you compare Jupiter and Saturn, you actually realize that they don't look that similar, right? Because you see that for Jupiter, most of the solutions suggest that the heavy element mass fraction in the deep interior is quite low and relatively flat. And for Saturn, it's much higher, right? And it has kind of a gradient. It looks like that, of course, with the degeneracy, because as I said, different models come up with different solutions. But all these are valid solutions that satisfy the gravity data and other measurements. Okay, so we have Jupiter and Saturn, and we see that actually they are not exactly the same. So I cannot say that, Saturn is just a mini Jupiter. That would be unfair in terms of the heavy element distribution. Okay, what else? Another issue is that I told you that formation models do predict composition gradients, but to be fair, if you see what is predicted from formation models compared to structure models that are constrained by the gravity data, they don't agree that well in the sense that formation models predict a steeper composition gradient compared to the structure models. Of course, one can say that this gradient could evolve thanks to, let's say, convective mixing, but still we have this disagreement. And one of the things we started to think is, actually, is it possible to create these composition gradients that are predicted by interior models from a formation perspective? And the answer was, well, not easily. We really didn't manage to make them, flatter and also going quite far out within the planet. So we really tried, you know how it is when you do modeling, you can play with the parameters, right? We know so little, and nevertheless, we couldn't find solutions. So we realized that there is a little bit of a tension there. So we started to look at that. So just to make a small break, so we have questions, but we also solved many things, right? So I think we really made progress in the last few years that we can really say that we understand the internal structure of Jupiter and Saturn better, and now we need to reflect this information or this knowledge on giant exoplanets. But of course, there were still kind of key questions or key challenges in the field. And one of them is why Jupiter and Saturn differ in mass and composition. And then I showed you the accretion model that shows the formation. And I told you, okay, at some point you reach your desired mass. But what is the mechanism that actually stops the accretion? We also still have the challenge of forming Uranus and Neptune. I didn't talk so much about them, but this is a key challenge in planetary science, especially now when we know that they are so common. We also know the giant planets are less common in the galaxy. Why is that? And at the same time, we see that there are many intermediate mass planets that are very diverse in composition. So although kind of we really solved some questions, this thing kept bugging me for a while. And then I thought, well, actually, how do we define giant planets? I mean, maybe we just have some kind of a misconception there. And then I started to think, can it be that Saturn is a failed giant planet, that it never reached this point of runaway gas accretion? So I really thought about it for a while, but I managed to take one semester sabbatical, so I could finally write this paper. So I did write this paper that basically suggests that Saturn is a failed giant planet. So, okay, I don't know if that's the answer or not, if it's a really failed one, but maybe bear with me for the explanation. So here, again, I show you these different phases, right? So the idea would be that Saturn never reached this point of runaway gas accretion. Okay, and I remind you that the many exoplanets, the intermediate mass exoplanets that we see, they have composition that is around that, right? So this is basically phase 2 in terms of the formation process. So it's when you accrete a bit of heavy elements, but accrete hydrogen, helium gas in an increasing pace. Okay, so. And again, I still want to understand what stops giant planets from growing further, right? So people who work on gap opening in disks, they find that most of the time the mass for gap opening is around Jupiter mass. But then Saturn has a Saturn mass, which is 3 times less than Jupiter. So if you have a mechanism and they form in the same disk with the same viscosity, this kind of similar physical properties, why didn't it happen to Saturn? I mean, it should have grown also to a Jupiter mass. Okay, so right, it makes you feel a little bit uncomfortable if it's just happened that then exactly the disk disappeared. So one way to solve that problem would be to say that this phase actually really does take a very long time. So only just a few planets that manage to grow fast enough end up in the runaway gas accretion phase. And that, by the way, also would explain why they are not so common in the galaxy, because you kind of need to be lucky to grow fast to become a gas giant planet. So when it came to Jupiter, then I realized that we had 2 studies further back when we looked at the formation of Jupiter. It was about Jupiter and trying to see how we can fit the right composition. And the idea was that that the core was formed by pebble accretion, so fast pebble accretion. But then there was a phase that delayed runaway gas accretion by accreting planetesimals that provide energy to the protoplanet that again delays the cooling. And as I said, delaying the cooling would kind of delay the point where you reach runaway gas accretion. And in a paper with Giulio Venturini in 2019, we looked at the heavy element mass fraction as a function of mass. Yeah, so this is in log scale, and this is Jupiter, and and how it changes, right? So this is the bulk, how it changes as the planet grows, and we consider different, disk properties and different growth rates and so on. And this is what we got. And what you see here in the green is to try to fit the metallicity of Jupiter. But then when I was thinking about Saturn, what I found very interesting is that, first of all, if you think about the metallicities, you really see these, three different cases, let's say. We really have the core formation where we have the bulk metallicity of the planet quite high, let's say up to 90%. Of course, it's a bit arbitrary, but let's say. Then we have phase 2, where we have diverse metallicities. And then we have phase 3, where suddenly the metallicity of the planet drops quite substantially. And this is a more hydrogen helium-dominated object. And what was really interesting was this drop, which actually occurred at Saturn mass. So I thought, wow, that was a model that was aimed at explaining Jupiter. So can it actually be that Saturn just did not reach this right part of the diagram? So I was looking into that and did these calculations with different accretion rates and tried to get a model that you delay runaway gas accretion, where you can still accrete enough heavy elements during phase 2 that you delay the point where gas accretion takes place. And you can see this occurs at around Saturn mass. Of course, it's model dependent, and you can play with the parameters, but this seems to be working. So in a more general perspective, here you can see what we would expect from this kind of formation scenario. And I put the planets in the solar system to convince you. So here again, we have the heavy element mass fraction as a function of planetary mass, and you can see the curve of the heavy element mass fraction and how it changes with mass. And you can see that here we have Uranus and Neptune. They have some hydrogen helium, but most of their composition is heavy elements. Okay, maybe water, methane, we don't know, but it's really heavy element dominated object. Then we have Saturn somewhere here with a metallicity of, let's say, 20%, and then we have Jupiter here. And it all fits the internal structure model solutions of the outer planets in the solar system with one kind of simplified model. So that was very encouraging, and here you can see the same idea. That's the planetary mass as a function of time. And in order for this model to work, you need that the core formation timescale is fast. Let's say cores are formed by pebble accretion, but that this intermediate stage of what I said, it's called phase 2, which increasing hydrogen helium accretion takes a few million years. And then here we have Saturn, and then again, if you grow fast enough, or if you have enough solids in your formation location, you will end up in being a gas giant planet. And this, of course, because it's a dynamical process to some extent, this also takes not very long time. So most of the formation process of giant planets is here. But if this stage takes a few million years, it actually explains really well why most of the objects that we see in the galaxy have compositions that are here, because they didn't reach runaway gas accretion. Indeed, it is consistent with the fact that we don't have so many gas giant planets, and it is also consistent with the fact that the compositions of intermediate mass planets are very diverse. So I was very happy about this explanation. Of course, it's simplified, and again, the details matter, but to zeroth order, it gives a very nice explanation for the outer planets in the solar system. Okay, so just to say here, really this formation model can explain what we see in Jupiter, Saturn, and Uranus and Neptune. So as I said, this is why it's very nice. It's very, very intuitive. And from exoplanet perspective, or from the disk or from formation timescale, again, since we now know that most of the disks just survive a few million years, then it explains, again, the low occurrence rates of giant planets. It's just because if it takes them time to reach this runaway gas accretion, then most of them will not end up being gas giant planets. So again, it also makes sense there. And what about the properties, the physical properties of giant exoplanets? So actually, interestingly, if you put exoplanets with very accurate measured mass and radii, you can see that the mass radius diagram or the behavior changes at around Saturn mass. And this is because in this side of the diagram, basically you can see that the curve becomes kind of flat. And this is what happens when you have degenerate matter. So then you know that even when you increase the mass of the object, the radius doesn't change. Well, on the other hand, on the left, so lower than Saturn mass, we see that at a given mass, there are very different sizes of planets, which tells us something about the diversity in composition. But I don't see it here, which suggests that in this side of the diagram, the composition of the object is dominated by hydrogen and helium, while in the left side, it can be anything. It's much more diverse. So again, this is kind of a hint that something occurs at around Saturn mass, so at around 100 Earth masses. Is it exactly 100 Earth masses? Of course not. It can easily be, plus minus 20 Earth masses, and of course it depends on the actual planetary system. But I think that the concept itself is probably robust. And again, interestingly, people are looking at these empirical mass-radius relations of exoplanets, and in all the studies, different studies, they really find a transition in the mass-radius relation at around Saturn mass. And it's a completely different, independent way of thinking about it. And it is still consistent with this model, that maybe something is happening at around the mass of Saturn. And recently, there was a paper that looked at the composition of giant exoplanets. And they plot this distribution. So here you see the bulk metallicity of giant exoplanets versus planetary mass. This is also in log scale. And they took the curve from this model and put it on the figure. And of course, there is a spread. But up to the place where we stopped, well, it fits the trend really, really well. So, well, is it by chance? Well, I hope not. I think not. It really makes sense. And I think it's a nice way of showing how we can really use these different perspectives of solar system science and exoplanetary science. Okay, so let's go to the question. So what is a gas giant planet? Well, if you ask me, it's a planet that is more massive than about 100 Earth masses. So at around Saturn mass. And the other thing is that its composition is dominated by hydrogen and helium. So I would say that everything that is lower in mass should not be dominated by hydrogen and helium, but should have a non-significant amount of heavy elements. And again, this nicely explains the differences in relative enrichments of the solar system outer planets, the fuzzy cores of Jupiter and Saturn that we see that they are quite extended because you have a longer phase to accrete gas and solids, the transition in the mass-radius relation of exoplanets that we see, and also the bulk metallicity of giant exoplanets that I just showed you. Okay, so why is it important? Why should you care? Well, I think you should care because it's really, we are in the direction of better understanding the formation of the solar system. It also kind of predicts what composition we can expect at different planetary masses. It also hints that the formation timescale of giant planets is longer than what we typically thought. So that's, of course, links to observation. So maybe if we see a very massive young giant planet, maybe it is not formed by this traditional mechanism. And probably there are other implications. Okay, so I have some conclusions. So giant planets are complex. Both formation and internal structure models of giant planets in the solar system and probably also in other solar systems tells us that these planets are non-homogeneous, not fully convective, and have these fuzzy cores or composition gradients. It is therefore very, very important to connect planet formation, thermal evolution, and internal structure because they all kind of affect each other. And as I said, the transition to giant planets occurs at about Saturn mass, and this can explain nicely the trends that we see in the solar system, but also around other stars. Okay, so what's next? And then I will be done. Okay, so in terms of theory, we really need to work hard to have this unified theoretical framework of this formation, evolution, and internal structure. Of course, we are talking about different accuracies, but we see the connection between them, so we should work more on that. We really need to reflect our understanding of the solar system, planets, on exoplanets, and vice versa, because again, we have very different and complementary type of data, and we should learn from each other. We also need to better understand the theoretical versus observational uncertainties, because now with really great missions, we start to get very small observational uncertainties, and sometimes the theoretical uncertainty is larger. So I think we need to understand what's going on there. Well, if I have a wish list of observations I would like to get, well, we really need to understand better the mass-metallicity relation of planets, and also how it changes with radial distances. We need to understand the connection between the atmospheric composition of and the bulk composition of planets. Now we have JWST data, we are going to have Ariel data. We are going to get measurements of the atmospheric composition, but we need to understand how we link it to the bulk composition. We can, of course, go better in terms of chemistry. You know, I always say heavy elements, but heavy elements could be iron, could be rock, could be water. Of course, we could start to distinguish between, you know, volatile materials and refractory materials, and some people are already working on it. And of course, also when it comes to different luminosities, different masses of the host stars, ages, and so on. So there is a lot to do. We are not going to be bored anytime soon. And I will just finish with a movie that kind of shows you the formation process from the collapse of molecular clouds up to the formation of a planetary system. Thank you very much.
All right. I will open the floor to questions as we enjoy this movie, especially from students and postdocs.
Should I continue with the movie?
Is there more?
There
Do
is
you want to
more.
show it
There is
all?
more.
I have
Just
to
a
go
little bit more. Okay.
We can enjoy it.
Here we have grain growth and sticking, formation of larger objects, planetesimals. Giant impacts. And the formation of a planetary system. Actually, the movie continues also with, you know, life on Earth and so on. It's very nice. But I'll stop with that.
Thank you very much for the amazing talk. So my question was a bit on the observational side. So you were linking the fact that we don't see that many hot Jupiters to the fact that they must be because of some process that is not that common, right? And you mentioned that hot Jupiters are found both very close to the star and very far away as well. So I was wondering, could that be for some reason due to some observational bias? So if there is a Jupiter further out, you would not see a transit, right? At least the probability of seeing a transit would be much lower, and that would be
Okay.
a bias.
Good question. Very good question. Okay, so to be honest, I did not say actually hot Jupiters or hot giant planets. I just said giant planets in general, right? Because indeed, when you look at small radial distances, we know that there, you should see them, right? And even there, when you should see them very easily, we see that they are not so common, right? We are talking about a few percent compared to the intermediate size planets. So in small radial distances, we know for sure that they are less common. Okay, what happens at larger radial distances? This is going, there are radial velocity measurements for a very long time. They also seem to be less common there. We are, in terms of direct imaging, I think it's still relatively new. Also there, the very cold, super cold, like HR 8799, they are also seem to be very rare. So I think it's probably something that could be universal, but of course it depends, right? Depends on the hot star, depends on where you are exactly in the disk. And then I would say that it can also hint that some of the objects that we see were not formed by the standard model, so by co-accretion. I think now we have some indications that disk instability could also operate in some planetary systems. So personally, I'm agnostic. I think we need more data. And as you said, we know now what is going on much better. For the closed-in planets, what is happening further out, we need more time and we need more observations.
Just a bit of a follow-up. So you said that in very close to the star, we know that there are less these gas giant planets, right?
But we don't think they formed there, right? We think they migrated there.
Yes, exactly, which means that maybe most of these are further out and we just don't see them.
Say it again?
Maybe most of them are just further out and we don't see them.
Right, but as I said, we have radial velocity measurements for let's say a few decades now, and they also indicate quite low occurrence rates. But you're right, understanding exactly what is happening post-formation and how it shapes the occurrence rate of planetary systems, we cannot say things with huge robustness because we are still exploring. Yeah, I don't know, we have to see.
Hi. Yeah. So, sorry. You kept comparing your models to already formed planets, but now we're starting to hopefully see more and more protoplanets embedded in disks. How do you think this can help constrain your models, and what kind of observables are you looking forward?
Yeah. So actually, these kind of observations, they challenge these models because, as you know, there are some disks that seem to have a planet, maybe a giant planet there, that are quite young, which would be inconsistent with this idea that giant planets take, a few million years to form. So if I really want to come up with an answer, I would say, then maybe they formed by, by disk instability, by GI. Then if we don't like GI, I would say, well, it depends on the local conditions. Because, of course, if you have massive disk or you have a large, or if you have many heavy elements that lead to very fast accretion rate, it could also lead to faster formation. So in the end, I think there is a distribution, right? There is a distribution of initial conditions. And when we look at protoplanetary disks, we see that. We see the complexity and diversity of disks. And then when we look at the exoplanet population, we also see diversity in composition. And to me, it makes total sense because you have different formation environments, so you will end up forming different planets. How exactly we can combine it? Well, we have some knowledge gaps in between, but I think the more information we have about these disks and the better information we have about the masses of the objects, of course, would be helpful to further constrain formation models.
Thank you, Ravit, for this fantastic overview of the core formation scenario. You mentioned twice now the gravitational instability and so the alternative, and I was wondering why these anisotropy. So is is it so strongly disfavored to say it's just the gravitational instability in the disk that can also contribute a bit to the diversity and to the population of giant planets?
Yeah.
Or what is the current state here?
So I think it depends on who you ask. Personally, I think that the disk instability model should not be totally dismissed because we have now some observations that could support it. Because I think most of the calculations in core accretion indeed tell you that at some point you open a gap in the disk. So it's actually not easy to form objects that are more than, let's say, couple Jupiter masses, but we see that they exist, right? So personally, I think the ones that are far out and around and have very young ages and high masses, they are good candidates of disk instability. Probably there is an overlapping population, and I would say that the lower mass end is probably core accretion. I think, the disk instability deserves more attention. We are back now at exploring that, also doing population synthesis models with disk instability, but I don't need to tell you how complex the process is and how much it depends on parameters. And of course, it's very hard to come up with a predicted population because it really depends on the local conditions, but we are on it. I think it should not be dismissed. I think for up to a Jupiter mass, it's probably core accretion. At higher masses, I would say the disk instability is a reasonable candidate.
More questions?
Thank you very much. Very nice talk. I actually have two questions. So one is you presented us that you have the Saturn maybe a failed gas giant, and I was just wondering why you say it's failed or could still be in the process of becoming a gas giant, because the time axis you said is very interesting. And the second question I have is on the composition. You showed us that if you completely have hydrogen helium, and you have a line, and then underneath that line we have Saturn and Jupiter, but you also showed in one of your figures that there were lots of points above the line, and I was wondering what these points then would be.
Okay. Okay, so two quite separate questions. So for your question about, how do I go back here? Right, so about Saturn being failed, well, it's failed because we don't have a gaseous disk around us anymore, right? So it's over. Whatever you managed to accrete, great, now it's too late. So the idea is that Saturn, as well as Uranus and Neptune, are kind of failed giant planets. It just formed, the formation process took too long, so they never reached this point of runaway gas accretion. So then they don't have a chance anymore. So, well, there is always enough gas. I mean, there is the gas mass is high, but the idea is that you need to form a heavy element core early enough that it has enough gravity to start to accrete gas. So if your growth rate is too low, you will not reach this point. So that's basically the idea. So Saturn, also because it's further out in the disk, the solid surface density is lower, so it takes longer to form. And for Uranus and Neptune, it's even further out, so the growth rate is even lower, and this is why they are even more failed gas giant planets. And your second question was about the mass-radius relations that I showed you. So the answer is that these are the hot Jupiters, the inflated Jupiters. So the ones that are here basically have sizes that are much larger than what you would expect from a hydrogen-helium composition. So then we know that they are inflated by some kind of mechanism. There were different mechanisms that have been suggested, but we are still working on that.
Sorry, I have a question. Does that mean they're all interior, like very close into the star?
Yeah, so the hot Jupiters are typically very close to the star, and then it could be so it could be ohmic dissipation. Some people say, well, it could be an opacity effect that delays the cooling. Some people say, well, maybe it's composition gradients that make them non-adiabatic and heat transport very inefficient. At the moment, there is no model that actually fits all the data. Maybe it's a combination. Maybe we are not really understanding something fundamentally. I don't know.
Okay. One last question.
So I wanted to pick up on something you said about the outer disk having like less stuff, and because of this, your growth is slower, because of which you fail to become a gas giant. So that would essentially just predict that you would have this hierarchy everywhere, right? You have some sort of hierarchy everywhere where in interior you form some Jupiter, and further out, if you have multiple planets around a star, you would start seeing lower and lower mass planets. And is that the case?
To some extent, yes. In a zeroth order way, the answer would be yes, because the density distribution in a disk is really decreasing with increasing radial distance. So then, as I said, to zeroth order, the answer would be yes. If you start to think about, ice lines, it might be different. If you start to think about, dynamical interaction, it can also be different. So, if you have pressure bumps in the disk and you can suddenly collect many heavy elements, it would change this kind of very well behaved point of view. But to zeroth order, I would say that that's the case. I mean, the further you are, the less material or at least heavy elements you have to grow. And we do understand, at least we think we understand why our solar system looks like it does, because, Jupiter is located in a place where you think that it is, beyond the water ice line, which suddenly increases the available material or the amount of heavy elements. Of course, okay, if you think about pebbles, I should just say it's also quite different, because then you have flux coming from the outer part of the disk to the inner part of the disk, and that also makes everything more complicated. So it really depends. To be fair, I would say that it depends on the model you consider and the accretion rates that you consider. And of course, also dynamical interaction, gravitational interactions can take place later, and that would completely change the architectures of the system.
Great. So I will just announce that there will be drinks with the speaker, and then followed by dinner with the speaker, all at Dorfschenke, and there's still spaces available, I've been told, in case anyone wants to join. And with that, let's thank our speaker one last time. Thank you.